Okay, now let's start the chapter 24, which is one of the most important chapter in our entire course. So we'll take it very slow, step by step, and we'll spend a significant time on this chapter. And of course, because due to the importance of this chapter, we will have it in, we'll have a lot of questions in this chapter for your exams, including midterm and the final exams. Okay, before we start, how many of you have read the chapter 24 of the Gauss law? Have you read the textbook? No? Okay. It's okay, but if you can read it before the lecture, I believe it will be even more helpful for you. Okay. Gauss law is a very important law in electrostatic. When we do the calculations of electric field, in a lot of cases, if you can use Gauss law, then it makes your calculation simple and easy. Before Gauss law, we have already learned another basic calculation of electrostatic forces and the electric field. Do you remember that law? So how to do the calculation of electric field and electric force based on the point charge? What's that law? We use the equation to calculate the force between two charges, or the electric field surrounding a point charge. What is that equation or that law?
Coulomb's.
Exactly. So that's Coulomb's law. And the equation is simple. It's a constant, which is 4 pi epsilon, then Q1 times Q2 over R squared, the distance squared. So that is Coulomb's law. It solves a lot of problems. When you have a point charge in space, you can calculate the electric field in the space generated by this point charge. But if you have multiple charges, several charges distributed in the space, still you can use Gauss law to calculate the electric field or electric force on a certain position. You just need to calculate multiple times. You get several vectors, and then you do the vector sum. You will get the net force or the net electric field. So that is called superposition, the principle of superposition. You can just add, of course, it's a vector add several electric field or several electrostatic forces. Here in this chapter, we're going to learn an even more general way of calculating the electrostatic force and electric field. This is called Gauss law. We will introduce the Gauss law little by little. Okay, this reading questions seems like we haven't read the book, so I guess you're not able to answer those questions. And let's start directly to the content. So first of all, let's take a look at a simple case, which is electric field of a charged cylinder. Suppose we know only two things about electric field. First, the field points away from positive charges toward negative charges, and then electric field exerts a force on the charged particle. And then what can we deduce about the electric field of an infinitely long charged cylinder? So first of all, can you imagine what is the electric field line distributions for such a charged cylinder? And the cylinder is infinitely long. Yeah, I guess most of you have already had a picture in your mind. If you look at it in a cross view, it might be similar to a point charge. It's going like from the center and going out to the infinity far away positions. But if you look at it in a side view, it will goes out straightly to the infinity far distance. But now let's try to illustrate the field lines first. The first thing we know is the charge is positive, and this system, it has a cylindrical symmetry. We will use this symmetry to deduce the electric field. Okay, let's see, what is cylindrical symmetry? An infinitely long charge, the cylinder, is symmetric with respect to three things. First, translation parallel to the cylinder axis. Because it's infinitely long. So, for example, if you make a cut at some position, at any position of this cylinder, make a cut which is a perpendicular cut to the length of the cylinder, you will have symmetry. You have two parts, the left part and the right part. So they are symmetry, right? Because it's infinity long. On the left side, it's infinity long, and on the other side, it's also infinity long. So when you make a cut, you get two symmetry parts. This is the first symmetry. The second symmetry, rotation by an angle about the cylinder axis. So now you have a, let's say, a cylinder or a tube. It's infinitely long but straight. So if you rotate it in a certain angle, what you get after the rotation should be exactly the same before the rotation, right? If it's a perfect cylinder. You can imagine if you have a cylinder in your hand, if you rotate it, if it's perfectly made by some certain uniform material, if you do a rotation, the feature doesn't change at all. If you rotate it based on the based on the center axis. So this is the rotation symmetry. Okay, the third one, reflections in any plane containing or perpendicular to the cylinder axis. And next one, the symmetry of the electric field must match. It missed one thing. It didn't describe in word, but it's shown in picture. There's also a symmetry, which is a reflection in plane containing the axis. So as shown in this picture, if you have a cylinder here and you have a plane to cut it, and this plane is containing the axis or the center of the cylinder, then when you make a cut, no matter which direction is this plane, it could be a horizontal plane or vertically distributed plane, or it might be in an angle, but as long as it contains the axis or the center line, then after this cut, you should get two halves of the cylinders, and those two halves should be the same, or should be exactly in the symmetry. So that's another symmetry of cylinder, or cylindrical symmetry. Okay, if we understand those 4 types of symmetry, then let's look at the charge distribution. If it's distributed uniformly in a cylindrical and infinity long cylindrical cylinder, then the field lines, which is one important feature of this charged cylinder, should also have those types of symmetry. Now, let's based on the symmetry, let's try to deduce what should the field line look like. First of all, let's imagine the field lines. Could the field lines look like the figure shown below? Not possible. Why? All right. So it doesn't follow at least one of the symmetric distribution. For example, if you make a reflection plane, or if you make a cut at the position of dashed line, as we talked before, when you make a cut, the left part and the right part, they should be symmetric. However, if the field lines distributed in an angle with your cylinder, then when you make a cut, what happens? You will see, if you make a cut or if you do a reflection based on this cutting plane, you will have something like that. That's a different system. From previous system, your electric field goes in the direction of right direction. It has component of going to the right, but after the reflection, it's going to the left. So that's not a good symmetry. So that's impossible for such a system. So that means, therefore, the electric field of a cylindrical symmetric charge distribution cannot have a component parallel to the cylinder axis. So if there's no parallel component, then what's the direction should the electric field pointing to? So it has to be perpendicular to the axis of your cylinder axis. Only in that way you can do a reflection at any cutting plane, and it doesn't affect the distribution of the field lines. Okay, another thing. Could the field lines look like the figure shown here? Is it possible? No, possible. Because we talked about the other symmetry for a cylindrical distribution, which is if you make a cut or have a plane which goes through the center line of the cylinder, and then the reflection should be the same as the original distribution. Now, if we do a reflection based on such a plane, what we see is this. So actually, it's different from the previous one. The previous one is in that direction, but after you do a reflection, the direction has been changed. So it's impossible, or such a electric field distribution is impossible, and the cylindrical symmetric charge distribution cannot have a component tangent to a circular cross section. So there shouldn't be any tangent component, then there's only normal component. It has to be perpendicular to your cylinder. Okay, based on those symmetries and those impossible distributions, then what we can conclude is an infinitely long charged cylinder must have a radial electric field as shown below if you see this inside the view, what do you see is here. And if you look at it in the, let's say, across view, it is showing in this direction. Does that make sense? Yeah, so that's the field line distribution of charged cylinder. And we take this cylinder as an infinity long, which is ideal case for the cylinder. Okay, that's the first symmetry, which is cylinder symmetry. Now let's see the other symmetry. There are three fundamental symmetries. The first is planar symmetry. So here shows the planar symmetry. If you have a plane, which is shown here, and then the planar symmetry involves symmetry with respect to translation parallel to the plane. For example, if this plane is infinitely big, so if you move this plane from the left to right or right to left, or move it in any directions in this plane, it's still in this plane. If you do a translation, the feature of the plane doesn't change at all because it's infinity long. You can say here is the center. If you move the center there, you can say there is the center. So actually there's no center because it's infinity. So you can just move it in this plane without changing any features. That's plane or planary symmetry. And then the rotation about any line perpendicular to the plane doesn't make change. So you have infinitely big plane, and if you choose a line or axis which is perpendicular to any to the plane, but at any position, and then you do a rotation for the infinitely big plane, there's nothing will be changed. Does that make sense? Because it's infinity big, so anywhere could be the center. You can rotate it based on this position or that position. When you do the rotation, the feature doesn't change. And then reflection in the plane. If you do a reflection in this plane, let's say you have infinitely big plane and you get any line as a cutting line, and you do a reflection, this plane should have no change. So that's the planary symmetric. So that's the planary symmetric, and then we have introduced the second symmetry, which is cylindrical symmetry. We're not going to introduce more about that. We have introduced a lot of details. And then the third symmetric distribution is spherical symmetry. Spherical symmetry involves symmetry with respect to first, rotation about any axis that pass through the center of point. For example, if you have a perfect sphere, you can choose any lines as the axis, as long as this axis goes through the center of the sphere. Then when you do any rotations, no matter how many degrees you rotate, this sphere should have no changes if it's a perfect spherical symmetry. This is a rotation symmetry, and then reflection in any plane containing the center point. Again, if you have this sphere here and you have a plane which goes through the center of this sphere, and then if you do a reflection, the sphere doesn't change. It's the same. So that's a perfect spherical symmetry. So far, we have introduced all of the fundamental symmetries: planary, cylindrical, and spherical. Okay, Now let's introduce a little bit about flux. We have introduced something about the geometry based on symmetries. And now let's get back to physics. First of all, what is flux? Flux is a concept which is related to the concept of electric field. Let's consider a box surrounding a region of space. We can't see into the box, but we know there's an outward pointing electric field passing through every surface. Now, please see this box. You don't know what the charge distribution in the box, but you know there's some electric field or field lines going out of the box. That's shown here. Then, since electric fields pointing away from positive charges, we can conclude that the box must contain some net positive electric charge. That makes sense, right? Even you don't know what's inside the box, but you know the field lines are always going out, then you should have some intuitive idea about the charges. It cannot be a negative charge, right? If negative charge, what happens? Yeah, it should be going inside the box, but now it's going out. Then that's telling us there must be some positive charges or net positive charges, which generating the field lines. But if you have different boxes containing different charges, one box giving you more field lines, the other one giving you less field lines. So how to describe the electric fields going out of the box quantitatively? Which one gives more quantitatively electric field lines, which give you fewer lines? How to calculate the field lines quantitatively? This is a flux. Flux means the field line strength times the square, times the area. That means the bigger flux means more field lines are going out. That's the very basic concept of flux. Let's see. So that's the opposite case. When you see there are field lines going in, you know there must be some negative charges inside. Now consider a box surrounding the region of space. We can't see into the box, but we see a lot of field lines are going in from one side and then going out at another side. In this case, there are field lines go into the box from the left and going out to the right. Since the external electric field is not altered by the contents of the box must contain zero net electric charges, because every field line which is going from left to the box must go through the box and get out of the box from the other side. So at the end, the let's say at the end, the box must contain zero net electric charges. So this is flux. Flux is the electric field times the area of your surface. Then let's talk about surface. Now we're introducing Gauss law, so we have to introduce the Gaussian surface. A closed surface through which electric field passes is called a Gaussian surface. So the Gaussian surface may be a real surface, it might also be imaginary surface. It could be just a theoretical surface without any physical surface. For example, if you have a point charge here, you can imagine there's a surface surrounding the point charge, which can make your calculation easier when you do some certain calculation. We'll introduce it later, how to draw a Gaussian surface and theoretically make your calculations easier. Okay. But before we introduce the Gauss surface more, let's first take a break. Let's take a short break, about 5 minutes, and then let's come back. Okay, shall we continue? Okay, let's continue. Gaussian surface. Well, this is blocking the view. Let me hide this. Okay. A Gaussian surface. A Gaussian surface is most useful when it matches the shape of symmetry of the field. We're going to use some Gaussian surface to do the calculations for electric field. So when you have some charge distributions, for example, those charge distributions may be very complicated, but in a lot of cases, you may have some distributions of the charges in some symmetry, like cylindrical symmetry or planetary symmetry, or at least you can take the distribution as some certain symmetry. It might not be perfect in real life when you solve the problems, but you can take it as some basic symmetry distribution. For example, if you have charges in a wire, you know the wire might be in a curvature shape or something, but at least when you do the calculation of a small part of the electric field line distribution for that wire, you can take that part of wire to be a perfect cylinder, right? Does that make sense? Or for example, if you have a charged object, which is not a perfect plane, it's a curved thing. It has some thickness, but it's a curved. When you do the calculation or some simulations of this object, when you focus on the small part, you can take it as a perfect plane, right? When it's very small, even though the whole plane might not be a perfect plane, may have some curvatures. The thickness may be thicker here, thinner there, but when you take a small piece, you will take it as a perfect, roughly a perfect plane symmetry or something. So we will learn some basic, let's say, calculations of electric features based on those symmetries. Those symmetries can be applied to ideal case, and also practically you can use it in many real cases. You just need to recognize which symmetry is the closest to your real problem. For example, if you have some small object, it might not be a sphere, but you want to calculate the electric field far away from this point, then you know you can take it as a perfect sphere because it's very far. You can take it as a sphere object and try to calculate the features based on spherical symmetry. Now here, let's see the first example. If we have, let's say, a cylindrical distribution of charges, which is shown here. Let's say this is a cylindrical charge distribution. You have a lot of charges. It's a straightforward, it's a straight line. And then you want to calculate the electric feature. What you can do is you can first find a symmetry or symmetric surface which contains a part of those objects. So the best symmetric surface you can find is the cylindrical Gaussian surface. And we call this Gaussian surface because we make a closed surface. If this surface is a cylinder and its center is centered as the charged object, then it has a perfect symmetry of electric distributions. This is the figure A, and figure B shows the side view and top view or cross view for the same cylinder distribution. And in another case, if it's not a cylinder distribution, let's say if it's a sphere distribution, a point charge can be considered as a spherical distribution. If you want to do some calculation of point charge, you can also draw a surface which is perfectly symmetric surface with a center at the center of your point charge. But here it shows a not perfect surface because not a perfect symmetric surface, because if you take a look at this surface, you will see, first of all, the field lines, it's denser here, but it's closer. I mean, the field lines are closer on this side, but less close on the other side. So that's not a perfect symmetric surface. In this case, the Gaussian surface doesn't match any symmetry. So in this case, this surface is not very useful to solve your problem. Yeah, please.
So does the length of the arrows matter, like how the electric field is working? Because like those are longer and then those are shorter, so just because it's wide.
Ah, okay, that's a good question. So for electric field, the length of the field lines or length of the arrows, actually it doesn't mean the strength or magnitude of the electric field. But there's another thing indicate the strength. Do you remember what is that? So which type of field lines indicate a stronger electric field? Density, exactly. When the field lines are closer to each other, you know it's denser. When they're far away from each other, you know it's weaker. No problem. For example, here, you know, the position here, the electric field line here is weaker than field line here because at the second point it's distributed closer or denser. Okay, that's the Gaussian surface. Now let's get back to the flux. First, let's have an intuitive idea of what is flux by using the flux of airflow. And then it's similar for the flux of electric field. Imagine there is a rectangular wire loop, which is shown here. And the area is A in the front of a fan. And then the fan is blowing the airs to flow through this loop. And then you can imagine the flow is maximum through a loop that is perpendicular to the airflow. If this loop is perpendicular to the airflow, it gets more airs go through. If it's parallel to the airflow, there's no air go through the plane, right? Go through the loop because it's parallel. If there's an angle, depends on the angle, the airflow go through the loop could be bigger or smaller. It depends on theta. So when angle or when theta is 0, there's when theta is 0, the airflow flux is maximum. But here we define the direction of the loop to be its normal direction. Let's see, this is a loop. The direction of the loop surface is perpendicular to the loop surface. It's a normal surface as shown in this figure. And here, if the normal direction of this loop is perpendicular to the airflow, then there's no airflow go through this loop. Then the flux is 0 when theta is 90 degrees. When there's a theta, when there's an angle, which is theta, then the airflow flux or the flux of the airflow could be calculated by using the volume of air per second, which is a V times A, but it's a dot product of two vectors because your airflow has a direction and your surface on the loop has another direction. When they have an angle, this angle could affect the flux. And then the flux can be calculated using this equation, V dot product A. This is a V. Dot product A. Have you learned the calculations of vectors? Like what's the difference between a dot product and a cross product? Have you learned that before? Okay, so then let's do not go too fast. We need to introduce a little bit about the vector calculations. What is dot product? What is cross product? So dot product is a product of two vectors. When two vectors has a certain angle, let's say vector A and vector B. So when you see there's an arrow above a letter, that means this is a symbol of vector. That means it's a vector, not a scalar. So if two vectors have an angle of theta, then we will say A dot product B equals to a scalar, which is A times B times cosine theta. So please notice that here, A and B are scalars. It's the magnitude of the vector A and vector B. We don't have any arrows above the A and B here. That means the dot product of a vector and another vector result in a scalar, and the scalar is and this scalar, the value of this result depends on the magnitude of vector A and vector B, and also the angle between those two vectors. If theta is 90 degrees, then cosine theta is 0, then the dot product is 0. When theta is 0, the cosine theta is 1, then you get the maximum value of the dot product. So for cross product of two vectors, that's even more complicated. So vector A cross product vector B, it results in a new vector. So let's introduce the cross vector when we use it in later lectures. But here, please remember the dot product for two vectors. It results in first a scalar, and then this scalar depends on magnitude of the two vectors and also the angle between two vectors. And it becomes A times B times cosine theta. So here, same thing. When you do the flux calculation, you need to find the angle between your airflow and the surface. Then use your airflow speed times the area of the surface times cosine theta. It's simply a dot product between the flow vector and the loop surface vector. Similarly, we can define electric flux. It's very similar to the airflow flux. The electric flux, phi, means it measures the amount of electric field passing through a surface of area A, whose normal to the surface is tilted at angle theta from the field. So again, the flux equals to the electric field dot product A, which equals to E times A times cosine theta. Please be careful that the direction of A. What is the direction of A? What's the direction of the surface or surface area? Remember that it's normal direction of your surface. If you have a surface in this way, and then the direction of your surface is in that way. It's perpendicular to your surface. Okay, let's do a simple calculation. Now we have defined the equation of calculating electric flux. Let's do a calculation of a flux. Now you have a surface, which is 2 by 2 meters. And then you have this flux, which is 100. 100 Newton per Coulomb. And then what is the flux go through this surface? Let's say the flux now is perpendicular, the electric field is perpendicular to your surface. Then what's the number? Okay, let's see. So who's going to choose option A or B or C or D? Okay, great. The answer is C, because we can simply use EA cosine theta. Here, what is E? E is here. It's the electric field. What is A? A is 2 meters by 2 meters. It's a 4 cubic meter, square meters. And then what is the cosine theta? What is theta? 0. What is cosine theta? 1. Okay, so you get EA cosine theta. Finally, you get 400 Newton meter squared per coulomb. Okay, now let's say if the plane is parallel to your electric field, then which one is your answer? Great. So what's the angle between your surface and your electric field? 90. Then cosine theta is 0. Perfect. Great, great. That's perfect. Now, okay. This one is a little bit confusing, perhaps. So which one is your answer? Okay, let's try. So who's going to choose A, B, or C, or D, or E? Okay, so the most difficult part is recognize the theta. What is the theta, right? I think everyone knows what is E. This is E. What is A? 4 by 4. Sorry, 2 by 2. It's 4. 4 meters squared. However, theta is difficult. So first of all, what's the direction of electric field lines? What's the direction of electric field lines? It's going to this direction. What's the direction of the surface? That's the final and key point. Perpendicular. Great. That's the direction of your surface. And this is, sorry, I didn't draw it in a good way. Let me erase it. So the direction of your electric field is going to the right. Then what's the angle here? 70. So finally, you should get C. So it shows you 20 degrees. That's a very tricky. So it's trying to making you consider the angle is 20, but that's not the angle between E and A. That's the angle between, let's say, the surface and the horizontal. So you need to really recognize what's the real angle between them. Area vector, we have already introduced the direction or vector of your surface. Please.
I have a question. In the problem, the lines were pointing to our side, and then
if the field goes in the opposite way, that's a very good question, guys. So actually, this remind us to a very important thing that I'm trying to hide, and I'm trying to tell you later. But now, since you asked, we have to face this question, which is when you have a surface, you have two directions, right? it could be perpendicular up or perpendicular down. So which one should we choose? In this case, we didn't say anything. By default, we say we choose the direction of the surface going in this direction. But in some cases, you can choose the direction of the surface in the opposite way. So any surface have two directions. Usually we define the direction of surface by our convenience. In this example, let's say when the air flows through an area, you want to calculate the flux of airflow. Usually we define the direction to be best similar to the direction of the airflow, so that you get a positive number. Otherwise, if you define it in this way and the airflow goes that way, then it's cosine something, this angle is greater than 90 degrees, you get negative values. But that's very tricky. So if we don't define the area direction, you may have two answers. In your exam, if there's a question that I don't give, I forget to give you the direction of the surface. So no matter which answer you get, positive or negative, I'll take it as right, because that's the problem of the question. It didn't show you which direction is positive direction of the area. But later on, we will have some default directions for Gaussian surface. For a surface which is Gaussian surface is always closed surface. It's always closed. It's not open surface, it's closed. We always define the positive direction of your surface to be going out. So in this way, you will have a unique direction of your surface. In a Gaussian surface, at a certain position, at this position, you may have two directions, going out and going in, which are all perpendicular to your surface. Only the going out direction is your positive direction of your surface. That's by default. We haven't get that point. That's in the later slides, but I'm glad you have been thinking forward. That's very good. So in this exam, if there's option says cosine, let's say, what's that? This is 70, then that's cosine 170 here. Then on the other direction will be, oh, sorry. If you use this angle, that's also right. For example, the electric field is going to the right, but your your surface is going down, then the angle is 110 degrees. If you use cosine 110, it's also a right answer, but you'll figure out it's a negative number, which is same magnitude, but negative.
So it's okay to have a negative electric flux even with an area? If the area in the square is an area, so a negative area is negative.
Yeah. So the area is always positive, right? We can't have a negative area, but the flux can. Because when you define the direction of area, let's take a more data life example. The same thing, airflow flux. The airflow flows in this direction, let's say, and then you have a surface here. You define the surface direction is that direction. Then you will get positive airflow, means the air flows in the same direction of your surface area or going out. But you may have some cases when the air flows in the opposite way, but still you define the direction of your surface is going to this direction, but the air flows in the opposite direction. That means when you define the direction of surface, you already define which is inside, which is outside. This is outside. When you do the calculation in this way, you're asking how much airflow is going out. If the airflow going this way, of course, the positive number is going that way, it's a negative number. So it's negative number of air flows out. Means some airflows are flowing in, right? So it could be negative. In a lot of cases, it could be negative numbers. Not only for airflow, think about the electric field. If you have surface which is closed, when you do the flux, if it's a positive number, it means there's some electric field going out. When it's a negative number, it means more field lines are going in. Simply means in your surface, you have some negative charges. So that's the positive and negative flux. Very good questions, actually. Okay, so here, this is the definition of area vector. Then we can define the electric flux to be E times A, but it's a dot product. When you do a dot product of two vectors, you can convert it into E, scalar E times scalar A times cosine theta. Okay, last slide. Let's solve the problem together, and then that's all for our class. The electric flux inside the parallel plate capacitor. Now here you have okay, the question is here, I think. No, where is the question? Sorry, it's not in the slide, but it's in the textbook. So, but technically now, if you have a question, it gives you the strength of your electric field and direction of the electric field, and then you know the area of your surface, and you know the direction of your surface. Can you calculate the flux? That's very easy, right? Just use this equation. E dot product A, they're all vectors. Remember to get the cosine theta and identify what is theta. Sometimes it gives you some degrees, but it might be misleading you, which is not the angle between surface and electric field. Okay, so that's all for our class today. Do you have any questions? Please. It will be the second week after the spring break. No problem.